welcome to our preliminary design presentation of our post-operative device for cancer removal in the Philtrum. My name is Caleb Yates. My partners are Audrey Wood and Olivia West. And today, this presentation is also brought to you by Dr. Seth Yellen, MD. So I'm a biomedical specialization here. I have patient care experience of about 150 hours involved with prosthetics along with basic orthopedic clinics. My scholarship
I have first-hand experience in the scope of this project because our client, Dr. Seth Yellen, is the surgeon of our test patient who also happens to be my mother. My previous BME projects include force analysis on the carpal and metacarpal using MTS, gait analysis,
So today's presentation is going to kind of start off with a background about what the problem is and kind of how the problem became and what we want to kind of accomplish with it. From there, we're going to go into the project design and description about how we're going to tackle the problem, what we kind of saw would help tackle the problem, and where we're going to go from there. Then we had a few designs we had in our heads, and we finally got down to a few, so we're going to talk about what those designs are and what they kind of do to solve the problem. From there, we're going to talk about our feasibility analysis and our merit analysis about what exactly made the project feasible and possible for us to do, along with what made a product better than the other one. From there, we're going to go to our design implementation about how we're going to go about actually creating the prototype that we decided. Our patent and safety considerations about where the device would stand within any other devices in the market, about if it's ever going to be too similar to cause legal issues, along with making sure the device is safe due to the fact that the body creates such harsh environments for external items. From there, we're going to go into the current market and budget analysis about what else does stand in the market and how this will compare to that, and how it will get a foot in the foot of the door with that market, along with how we're going to use our budget to actually do the project. And then from there, we'll do our proposed testing analysis of what we kind of want to do to make sure the device is to standards that we want it to.
So for this project, there is currently a need in the medical field that, as far as we know, has never been addressed. Skin cancer can occur anywhere on the body. Anywhere you have skin, you can get cancer. There's a Mohs procedure, it's a surgical procedure to remove carcinomas and melanomas. As you can see here, this is our test patient, figure 1. She had the Mohs procedure done on her upper lip, and the scar created, it's a little bit dark, I'm sorry, is all the way from the bottom of her nose through her vermilion. So what happened with this, the consequences here, were that the scar actually lifted her vermilion, it created an asymmetry, and it brought the vermilion toward the top of her nose, completely changing her post-operative appearance from her preoperative appearance. It's not something that you want to do. You don't want to look completely different just after having skin cancer removed. So the project is to address this in a way that is convenient for patients. Because right now, they have to use their hands and physically tug, and this is physician suggested, physically tug on the scar every single day to prevent that recession. Whenever you can, tug on it. But overnight, that's 8 hours where a patient can't consciously tug on his or her lip. And by the time they wake up the next morning, any progress that they may have made is gone. The lip is already recessed yet again. So we're going to use pressure and silicone to not only prevent the heavy scar that you've seen in someone untreated, but also to just encourage the wound healing in a healthy and natural way. So pressure fights scarification. How? In the medical field, it's already thought that pressure will decrease tissue metabolism and increase collagen breakdown within the wound. After surgery, collagen fibers are released and produced to the wound to help heal that tissue. And it's when these collagen fibers thicken and toughen and stiffen that causes scar formation. So the pressure aspect of our device is going to repeatedly break down the forming collagen and discourage the abnormal formation and encourage a more natural alignment, more natural healing position. Silicone. Silicone fights scarification. How? Soft silicone can form a seal around a wound by creating multiple contact points. By doing this, you're keeping good moisture in, bad moisture and debris out. The silicone that we're using is non-toxic, it has low thermal conductivity and low chemical reactivity. It's going to be safe, it's going to be atraumatic to the wound. And the silicone dressing over the wound is really going to encourage healthy healing. That's the whole point of the silicone.
So to kind of get into this project, of course, we noticed that our timeline we had to consider was from May of 2017 to about April 2018. And of course, for about 4 months, we brainstormed about how we were going to implement this pressure and moisture idea into a design. So after a few designs, we kind of started narrowing it down. Along with that, during our design, we also were able to converse with our client, Dr. Yell, and he gave some great ideas and suggestions that helped us kind of point us into another direction we weren't even thinking about. Along with that, we went into our feasibility analysis into exactly, of course, saying what was feasible and what made the certain devices feasible for us to do and if they passed it, along with the merit analysis as well. From there, we looked at our budget and exactly how we were going to build that and what it was actually going to take for this. Then we went into our IRB courses to make sure that all members of the team here were IRB certified for our human testing we would be doing, along with kind of what it would take for our application for that process. Then we had to go into our mechanical research about exactly how the device was going to mechanically work, the pressures, any type of sores we would cause with this, along with the actual rigidity of the material, which of course leaked into the material research which happened at the same time. From there, we looked at fabrication research about how we would even fabricate the design that we were going to go with and what it would take to implement that process. So upon approval, we will of course start ordering materials, start building our 3D models and designs, and of course the actual prototypes from the device, go into our testing, and then from there kind of continue to make sure that everything is up to standards that we want it to be. So for our technical approach, as we said, we wanted this pressure and to be kind of the forefront, and then the silicone to be right behind it, and to continue to make sure that this did what it needed to. So therefore the devices had to supply constant pressure to the area, along with being able to go to the certain area that it is, because not all the scars are going to be right in the middle of the Philtrum. So we had to make sure that it would be adjustable. So on the next following slides, we'll actually talk about the designs that we went with and what they kind of do to bring into these applications.
Okay, so this is design 1, and as you can see, it'll be made out of a mouth guard, which is right here, and it will be fitted to each individual patient to make it more comfortable, and there will be a bar magnet attached to the front of the mouth guard, and the magnet will be coated with silicone. Well, the entire thing will be coated with silicone to make sure that the patient doesn't get a weird magnet taste in their mouth or metal taste. And there will be a flap that will be attached right under the bar magnet, and right here is the side view of the mouth guard with the flap extended down. And the circular magnets that we would use in this design would sit inside of a little packet or a little pocket that's on the flap. And this is the second design, which utilized a very thin piece of metal that would be coated in silicone, and it would be molded to the upper lip for each individual patient. And then you would apply clips on either side to create a bending moment in the center of the lip to apply the pressure.
So in order to move forward with these designs, they had to be possible. And that's where we got our 4 feasibility criteria. The process of machining. We're 3 engineering students, and we needed to make sure that this was something we could actually accomplish. The complexity. Is the design complex enough that it's going to accomplish what we want? But on the flip side, is it simple enough that we can make minute changes based on the patient if we need to? The availability of the materials. Are these things that we can get our hands on within the timeline, first of all? And then the possibility of patent infringement. Anytime you're creating something that's going to interface with the human body, there's a possibility that someone else has thought of it. Can't have that happen. Luckily for us, both of our designs flew through the feasibility criteria, check marks across the board. So we were faced with the problem of choosing just one, and we decided to solve that problem with a merit analysis.
So for the merit analysis, we had to make sure, of course, that we had criteria that were important to the design and the success of the design. So of course, first one we came up with comfort. The device, of course, has to be comfortable. It has to be something that the patient would not mind wearing for long periods of time, because of course if the patient doesn't like wearing it, they won't wear it, and therefore the device kind of fails its purpose. And that's of course also why I got the highest rating, because of course if the device isn't used, then it has no purpose. From there we went into the form factor. As humans change, of course so do the lip dimensions change. So we wanted a device that would be able to kind of fit to a certain patient's application. And of course different sizes, from the width of the lip to the height of the lip to the thickness as well. And I got a 30 due to the fact that, of course, if the device is only able to fit one person, it doesn't open up the market as widely as we need it. The necessary maintenance, of course, we understand there is going to be some maintenance. Because as I stated earlier, the body makes very harsh environments, and therefore the device has to be able to withstand those. And along with that, you expect some wear and tear. Therefore, the device needs to have minimal maintenance that's not just cleaning this for almost an hour or so. After that, we had to look at ease of application. Was this device easy for a patient to be able to install and use on their own without having to use like a drill or something like that, or something extravagant to actually apply to themselves? So here we have our device 1, which is our magnet device. And the device 1 scored very high in comfort due to all of the silicone we're using and the mouth guard. Because the mouth guard would make it very easy for the patient to kind of hold in. It would kind of help everything stay in place. Device 2 saw a little bit less comfort due to the fact that those clips could possibly cause hot spots of pressure right where they're kind of connected. Device 1 had a lot of adjustability due to the fact that the little pocket that we're using, the magnets can be moved within there to more precisely put the pressure where it is desired, along with the actual mouth guard, which would need to be molded to the patient's teeth, causing more adjustability. The device 2 still saw some equal adjustability, but it was hard for those clips actually with metal, due to the elasticity of the metal, to precisely put as much pressure as you need to. Because of course if you almost try to bend a paper clip, it's hard to get to the exact point. From there, device 1 actually saw a little more maintenance in the device 2 due to the fact that there's so much more with it. Along with the teeth, with that mouth guard, you're going to have some more build up from plaque and other items within the mouth guard, so it's going to cause a little more cleaning to be performed. Whereas device 2 was fairly straightforward due to its small size, so it's very easy to kind of rinse off and kind of continue with your daily activities. Device 1, though, had the large ease of application, where of course it's very easy for a client to pop the mouth guard in and then just take the flap and fold it over the lip to allow for the magnets to secure where they need to be, along with easy to remove, where you just kind of pop the magnets off and remove the mouth guard. Device 2 saw a little bit less of ease of application due to the fact that you had 2 of these clips on the device and you'd have to remove one at a time, along with the device possibly causing hot spots even during the removal of the device due to the fact that you're going from a thinner layer of tissue to a thicker layer of tissue. After all of this, and taking into consideration the weight that we had, device 1 did show more problems than device 2 with a value of 6.8 compared to device 2 at a 5.6.
In order to implement this design, several steps must be taken. First, you would take the mouth guard and give it to the patient, and they would mold it to their mouth with the given instructions. And then you would sand the edges on the bar magnet with an aluminum oxide grinding wheel to prevent any sharp edges from potentially wearing the silicone down eventually and poking through and causing damage to the inside of the lip. We would create the flap with the pocket using a 3D printed plastic mold, which we'll get into in just a second. But you would create the flap, and then we would attach the flap behind the bar magnet, coat everything in smooth silicone, let it cure overnight, and then circular magnets will be placed inside the pocket based on each patient with the comfort and the effectiveness and how long they have to wear it for, and the pocket will be closed by the physician. And this is a hand drawing of what the flap would look like coming out of the mold. And the mold will be 3D modeled in SolidWorks, downloaded onto the 3D printer, printed, and then we will take the mold and run it through an acid bath to smooth out any of the imperfections on the plastic. And we pour the smooth on silicone and let it cure overnight, take it out, and then this dotted line right here would be a thin metal plate coated in a lubricant where we could paint on more silicone to make like a little pocket. And then the patient or the physician would put the circular magnets in and then paint another layer on top to close the pocket.
So now that we have a design and we know how we're going to do it, we have to really look further into these patents. The only thing that we found after looking far and wide that came anywhere close was the nasoalveolar molding device here, but there's a lot of differences. This device is used prior to surgery, not after surgery. It's used in order to make the reparation of cleft palates easier, and it's only used in infants. So kind of the same, not really the same. They both have intraoral and extraoral components, but because the device uses a retainer and not a mouth guard, we think we're safe there. And because we're taking magnets instead of bar, screws, and metal, we don't think that we're going to be in any legal danger with this device. The safety considerations and standards, super important anytime you're going to interface with human patients. The smooth-on silicone that we've chosen, we found the SDS sheet where it states that it's up to compliance with 2012 OSHA standards. No material in it is hazardous to the human body. It's also certified non-toxic and BPA-free. But for the mouth guard, there are no federal standards. The American Dental Association has created a seal of approval for mouth guards, but they admit that they have yet to give it to a mouth guard on the market. This is mostly just because there's no experimental data on what a mouth guard should do and how well a mouth guard does it. So for our mouth guards, we chose ones that seemed easy to mold and went from there.
So with magnetism and kind of that being in our design, we had to make sure, of course, it was also safe. So to kind of get into that, we looked at a study that Cornell University did to confirm that there was no issues. During their study, they looked at long exposure to magnets, and of course, turns out their study is a little more for industrial uses. So they looked at how long the human body could withstand kind of being within those magnetic fields. And we had to make sure that any of our magnets that we were going to use didn't see any results near that. So from here, you can see all the different magnets we're going to use by dimensions and their millitesla values. And the safe limit that they suggest is a 600 millitesla value over 8 hours. And of course, none of our magnets actually get close to that value. Therefore, we can kind of assume that our allotted time of 8 hours could be extended past that due to the weakness of these magnets.
Just in case you sleep in.
The performance of this device will be analyzed theoretically. Ergonomic data will be the main focus of the analysis, while the test patient and the 3 group members can comment on the comfort, application, removal, and the safety. The effectiveness of the device will remain theoretical because we can't just have a random person on the street undergo this procedure and potentially damage their self-confidence or anything like that just for us to have a human test subject. Her mom will be our test subject, even though she is past the window that it will actually help her scar. The final phase of this research will hinge on whether the theoretical data provides enough support to justify taking the project into a medical setting. Currently, there is no market on